This is an AQA GCSE chemistry paper. It's higher tier from June 22, paper 1. This question is about metals and non-metals. Figure 1 shows the outline of the periodic table. Element Q is a dull solid with a melting point of 44 degrees. It doesn't conduct electricity, so it's a non-metal. These are all properties of non-metals. Low melting point, dull, not conductive of electricity. So which section of the periodic table is most likely to contain element Q? Step line down here demarcates the division between the metals and the non-metals, so the answer here is D. Element R forms ions with the formula R2 plus and R3 plus, so that's a variable valency. If you can hear that noise, it's my cat meowing to be let in. Which section of the periodic table is most likely to contain element R? It's a transition element because of that variable valency, that variable number here. So it's going to be here in the transition part, so that's B. Give two differences between the physical properties of the elements in group 1 and those of transition elements. Remember, group 1, those alkali metals are soft compared with the hard transition elements. And those group 1 metals have lower melting points. You could also say that group 1 elements have lower densities and are less strong. Complete figure 2 to show the electronic structure of an aluminium atom. Here is a periodic table. We're looking here at aluminium and we need to look at this bottom number, which remember is both the proton and electron number. That is 13. So 2 electrons go into that first shell and then 8 in the next ones, and we need to count up to 13. There we go. Aluminium is a metal. Describe how metals conduct electricity. Answer in terms of electrons. So remember, aluminium being a metal has a sea of delocalized electrons. That delocalization means that they are free to move and that they can carry charge. Name the type of bonding in compounds formed between metals and non-metals. So remember, metals form a positive charge, non-metals form a negative charge. It is ionic bonding. Magnesium oxide is a compound formed from the metal magnesium and the non-metal oxygen. Describe what happens when a magnesium atom reacts with an oxygen atom. Now, magnesium is in group 2, which means it has 2 electrons in its outer shell. Oxygen is in group 6, so it has 6 electrons in its outer shell. Now the magnesium atom will lose 2 electrons in order to gain a full outer shell. The oxygen will gain 2 electrons in order to gain a full outer shell. And so in terms of the final charge, because it's lost those 2 negative electrons, it's 2 plus, oxygen is 2 minus, and we'll write that now. So the magnesium atom loses 2 electrons. Oxygen atom gains 2 electrons. Believe it or not, we're already up to 3 marks. Final ion charges are Mg2 plus and O2 minus. Sodium carbonate reacts with hydrochloric acid in an exothermic reaction. Here's an equation. A student investigated the effect of changing the mass of sodium carbonate powder on the highest temperature reached by the reaction mixture. So that's what we're measuring. Plan a method to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. So let's start with our variables. So what are we changing? Our independent variable. Is the mass of, use the formula here if you can't be bothered to write it out like me, sodium carbonate powder. And let's say we're measuring that using a balance. What masses shall we use? I'm going to use 1 gram, 2 grams, 3 grams, 4. Add known mass of sodium carbonate to a beaker and add 25 centimetres cubed of hydrochloric acid. Now the key thing here is this is a control variable, that volume of hydrochloric acid, because it needs to be the same every time. Ideally you'd use the same concentration as well. So let's write that there. And you can pick what numbers you want to here as long as you point out that they're the same. So I'm just going to go for 0.5 moles of hydrochloric acid. That really doesn't matter. You want to stir the contents of the beaker. You want to measure the temperature before the reaction and the maximum highest temperature reached. Give a piece of suitable apparatus using a thermometer. And that will be your dependent variable because that's what you're measuring. Make sure you repeat and calculate an average to improve the reliability. And then control variables, we already said use the same concentration and volume of hydrochloric acid. Let's use the same starting temperature because we need it to be a fair test. So where are these marks awarded? By talking about the fact that our mass of sodium carbonate powder has to be the independent variable, so it's what we're changing. The fact that we're using the same volume of hydrochloric acid each time and at the same concentration. Stirring is a mark. The use of a beaker is a mark. Measuring the temperature before and the maximum highest temperature is a mark. Repeating is a mark. Using the same starting temperature. We have definitely guaranteed ourselves 6 marks here. Figure 3 shows a line of best fit drawn through the student's results. Determine the gradient of the line of best fit. Use this equation. Gradient is change in highest temperature over change in mass. Give the unit. So just pick the easiest place to calculate this gradient. I'm going to go here and here. It's already told us what it is. So the gradient is change in y over change in x. So read this very carefully. That is 27. This is 23, which means that change in y is 4. Divided by x, that's 4 and 1.5. So that's 2.5. Sub in those units, it's degrees Celsius and grams. What's 4 divided by 2.5? 1.6, and our unit is degrees Celsius per gram. So let's steal that. Can't believe that's worth 5 marks. That's an awful lot of marks. Final answer, 1.6. The initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. Determine the initial temperature of the reaction mixture. Show your working. So we just need to get our ruler lined up, take that all the way down and then measure that. It is 20.7. Another student repeated the investigation but added sodium carbonate until the sodium carbonate was in excess. Which sketch graph shows the results obtained when sodium carbonate was added until in excess? So you'd reach a point where the hydrochloric acid was finally the limiting factor, so you'd see this plateauing, which means it's C. Figure 4 shows a reaction profile for the reaction of sodium carbonate with HCl. What do the labels X and Y represent? So X is energy. Do learn these endothermic and exothermic profiles. Y is your energy change. How does the reaction profile show that the reaction is exothermic? You have to look at these levels here. Because the products have less energy than the reactants, we know that it's exothermic. If they were higher up here, it would be endothermic. This question is about the different forms of carbon. Here's diamond. Describe the structure and bonding of diamond. So diamond is a giant covalent structure. With many strong covalent bonds. Remember, it's got a giant tetrahedral structure, which means that each carbon atom, tetra meaning 4, is bonded to 4 others. Why does diamond have a very high melting point? We can actually copy this wording here. So we pop that down, and then we say it has a high melting point because it's a giant covalent structure with many strong covalent bonds which require a lot of energy to break. It's a very neat way of writing this. Remember, my revision guide is full of these sort of succinct, perfect answers. Saves you having to learn the same thing 10 times. Figure 6 shows C70. What is the name of this type of molecule? This is fullerene. Just have to learn that football shape is fullerene. Molecules such as C70 can be used in medicine to move drugs around the body. Suggests one reason why the C70 molecule is suitable for this use. Lots of answers here. You could say because it's hollow, so it can act as a cage or carry the drug. It's unreactive, it's non-toxic. Calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. The Avogadro's constant is this. So we know we need 70 carbons per fullerene molecule, so we just do 6.02 times 10 to the 23 divided by 70 to get 8.6 times 10 to the 21. That's not really chemistry, that's just working out if you understand what the English is telling you. This question is about zinc and compounds of zinc. A student produces pure crystals of zinc chloride by reacting zinc oxide with hydrochloric acid. Here's the equation. The student adds zinc oxide to HCl until the zinc oxide is in excess. Give one observation that the student can make to show that the zinc oxide is in excess. Notice it's a solid, so you should have unreacted solid left in your beaker if it's in excess. Why is excess zinc oxide used rather than excess hydrochloric acid? Mainly because that unreacted solid can easily be filtered off. It's far harder to remove excess HCl. So excess zinc oxide can be filtered off, unlike excess HCl. Name one other compound that the student could add to hydrochloric acid to produce zinc chloride. Well, let's have a look at this reactant. Rather than the zinc oxide, we could have used zinc hydroxide or zinc carbonate. You could write the formula here if you prefer. Describe how the student should obtain crystals of zinc chloride from a solution of zinc chloride. This is all about evaporating some of that excess water to produce the hydrated salt. So we're going to start by saying heat to evaporate some of the water, leave to cool, and dry in a drying oven. Zinc chloride is also produced in a displacement reaction between zinc and copper chloride. Remember, displacement is based on which metal is more reactive. The equation for the reaction is this. Complete the ionic equation. So the way to do this is take that equation and split it up into its constituent ions. Then you want to delete the spectator ions. So they're the ions which appear on both sides of the equation. They do not partake in the reaction. So that's the chloride ion. And then just pop everything else back in. Why is zinc described as being oxidized in this reaction? We're going from Zn to Zn2+. So because of that, it has gained a positive charge by losing negative electrons. Remember, oil rig stands for oxidation is loss of electrons. Zinc has lost 2 electrons. Zinc and copper can be used with another substance to produce electricity. Complete figure 7 to show how zinc, copper and another substance can be used to light a lamp. Label the zinc, copper and the other substance used. So let's set up a simple electrolysis chamber. We want a beaker down here with 2 electrodes, one of which is copper, one is zinc. Complete that circuit. And in order for those ions to flow, we need an electrolyte. So that's your other substance. There's your copper electrode and your zinc electrode. This question is about groups of the periodic table. The elements in group 1 become more reactive going down the group. Rubidium is below potassium. Rubidium and potassium are added to water. Predict one observation that you would see that shows rubidium is more reactive than potassium. It's just going to be more vigorous. So think about those observations. There's fizzing, it moves around, it melts, it burns with a flame. So just make that more vigorous. So we're going to say burns with a bigger flame. Explain why rubidium is more reactive than potassium. So because rubidium sits below potassium in the periodic table in its group, it means that rubidium has more shells of electrons. And that basically means because when they react, they need to lose an electron. If you think about the fact that rubidium has more shells, it means that its outer shell electron is further from the nucleus, which means it's less tightly attracted. So it's more easily lost compared with the smaller potassium atom. So rubidium is larger and has more shells of electrons. This means that the outer shell electron is further from the nucleus and is less tightly attracted. Because there's more shielding. So the electron is more easily lost in rubidium. Complete the equation for the reaction of rubidium with water. You're going to produce rubidium hydroxide. Here's your ion for rubidium. There's your hydroxide ion. They're nice and balanced. We produce hydrogen gas. Have a look to see if it's balanced. It's not. We need a 2 here. So just to double check, rubidium has 2. Rubidium has 2. Hydrogen is 4. 2 plus 2 is 4. Oxygen is 2. That 2 applies to everything. So again, that is now balanced. The noble gases are in group 0. Which statement is correct? The noble gases all have atoms with 8 electrons in the outer shell. No, because the ones at the top don't. The noble gases have boiling points that increase down the group. That's true. The noble gases have molecules with 2 atoms. No, they're not diatomic. That's characteristic of the halogens. The noble gases react with metals to form ionic compounds. No, again, not true. So the answer here is the second option. The reason for that is actually quite an A-level reason, which is to do with increasing MR, increases the strength of the intermolecular forces. Table 1 shows information about 3 isotopes of neon. Calculate the relative atomic mass. Give your answer to 3 sig fig. So in order to do this calculation, you take the first mass number and multiply it by its percentage abundance. Then you add it to the second mass number multiplied by its percentage abundance, and so on and so forth. And then you divide the whole thing by 100. So let's write that out for you. Then double check the question's wording. It's 3 sig fig, so that makes it 20.2. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. Figure 8 shows a simplified version, which is the correct half equation for the production of sodium. We know we have molten sodium chloride, which means we have Na+. We're trying to produce molten sodium, so it has to gain an electron, which is reduction. Just scan down and look for that. It's this one down here. A mesh is used to keep the products of the electrolysis apart. Suggests one reason why the products of electrolysis must be kept apart. The reason for that is so that the products do not react to produce your original sodium chloride again, because that would be entirely pointless. Which type of particle passes through the mesh in the electrolysis of molten sodium chloride? Remember, electrolysis involves the movement of ions. Aqueous sodium chloride solution is electrolyzed in a different industrial process. 2 gases and an alkaline solution are produced. Yeah, this is actually the more normal. So if we have a look, if it's aqueous, it means you have these ions in solution. And then remember, the rules are that the least reactive positive ion forms. So compare sodium and hydrogen. Less reactive is hydrogen, so hydrogen gas will form. And then from a negative ion point of view, remember halogens always form preferentially, which means you'll have chlorine gas being produced with a sodium hydroxide solution left over. So these are your usual products of this electrolysis. Which 2 ions are present in aqueous sodium chloride solution in addition to the sodium ions and chloride ions? Wonderful, I've just mentioned that, H plus and OH minus. Name the alkaline solution produced. There it is, sodium hydroxide. Explain how the alkaline solution is produced. You should refer to the processes at the electrodes. I'm just going to say at the negative electrode. Let's give the half equation of what happens. So we're forming diatomic hydrogen, so make sure it's all balanced, which remember is reduction because it's gained electrons. At the positive electrode, we're going to form that chlorine. Again, that's diatomic. This is oxidation. And because those reactions are taking place, left over in solution is sodium ions and hydroxide ions. And for me, that's the neatest way of scoring those 3 marks. This question is about silicon and the compounds of silicon. The reactivity series sometimes includes non-metals such as carbon, hydrogen, and silicon. Silicon can be extracted by reducing silicon dioxide with different substances. The equation for one possible reaction is this. Explain what this reaction shows about the position of silicon in the reactivity series. So we have carbon reacting with silicon dioxide, producing silicon and carbon monoxide. Really what this is saying is that silicon is less reactive than carbon because carbon is displacing it. Aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon can be obtained by heating coal. Aluminium is obtained from aluminium oxide. Explain why aluminium is more expensive than carbon. The problem is that aluminium oxide needs to undergo electrolysis in order to purify that aluminium, and electrolysis requires a huge amount of electricity, and therefore much more energy is needed. Magnesium also reduces silicon dioxide. Here's the equation. Give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. Look at those state symbols, it's because they're both solid. So filtering won't work here. Can see a mole calculation coming. Calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilograms of SiO2. 5 marks. Okay, so what you want to do, guys, is steal this equation, just copy it out again. You must do this. Give yourself a formula triangle over here, which states that mass is number of moles times mR, and then get yourself ready with a table. Then substitute in all the information you've been given. We're after the mass of magnesium. We've been told we have 1.2 kilograms of silicon dioxide. Because that final answer needs to be in grams, let's get that 1.2 into grams. What about our MRs? They've kindly given us these numbers. So SiO2 is 28 plus 16 times 2, which is 60. To find the number of moles, cover the N. We're doing mass divided by MR. So that's 1,200 divided by 60, which is 20. Now let's look at the mole connection. There's an invisible 1 here, a 2 here, so we just multiply that number there by 2. And then our final step is to find the mass of magnesium by doing number of moles times MR. So that's 24 times 40, which gives you a final answer of 960 grams, and that's how you get 5 marks without too much stressing. Si2H6 is a covalent compound of silicon and hydrogen. Complete figure 9 to show the outer electrons. So hydrogen has 1 electron in its outer shell. Silicon has 4 electrons in its outer shell. 1, 2, 3, 4. 1, 2, 3, 4. Just double check that they're both full. Hydrogen needs 2 electrons in its outer shell to be full. Silicon needs 8. Si2H6 reacts with oxygen. The equation is this. 30 centimeters cubed of Si2H6 is reacted with 150 centimeters cubed of oxygen. Calculate the total volume of gases present after the reaction. So in order to do this question, it's a bit of a weird one, but if we look at the mole connection here, I can see that whatever my volume of Si2H6 I need 3.5 times of that of oxygen, look, because it's 2 to 7. So I'm going to do 3.5 times that 30 to get 105 centimeters cubed of oxygen needed. We've been told it's in excess, so how much of that will be left over? It will be 150 minus that answer, which is 45 centimeters cubed left over. And then just double check what else will be present after the reaction. We can ignore that because it's a solid. Again, just check the mole connection. It's 2 to 6, so I need 3 times as much of that original volume. So I'll be making 90 centimeters cubed of water, and then I add those two numbers together to get my final volume after the reaction. This question is about acids and alkalis. Explain why the pH of an acid depends on the strength of the acid and the concentration of the acid. Remember that acids all contain H+ ions, they're H+ ion donors. So first of all, pH depends on H plus concentration. The higher the concentration of H plus, the lower the pH. So that means acids like hydrochloric acid with pH of 1 have a very high concentration of H plus ions. Remember, the difference between a strong acid and a weak acid is that a strong acid fully dissociates. Therefore, donating those H plus ions in solution, so the stronger the acid, the lower the pH. A student titrated 25 centimetres cubed of hydrochloric acid with 0.1 mole of barium hydroxide solution. The student calculated the volume of barium hydroxide used was this. Explain why the student used a volume of 23.5 solution of barium hydroxide solution in the titration calculation. Let's use the table of results. So just have a look to see if there's any anomalous results. Yeah, this one. So let's show how they arrived at that volume by finding the average of these numbers. So that's how they arrived at that volume of 23.50. And 23.90 was excluded as it's anomalous. "25 centimetres cubed of hydrochloric acid was reacted with 23.5 centimetres cubed with 0.1 barium hydroxide. Calculate the concentration." Let's set ourselves up again, steal that equation. This time we need this formula triangle, which is number of moles is concentration times volume. Here's your table you'll want to use, listing NCV down the side. Let's sub in what we've been given. 25 centimetres cubed of hydrochloric acid is the volume. Make sure that's in decimeters cubed by dividing by 1,000. We know we have 23.5 centimetres cubed of barium hydroxide and that its concentration is 0.1. Start by finding the number of moles of barium hydroxide by multiplying the concentration by the volume to get 2.35 times 10 to the minus 3. Check the mole connection, it's 2 to 1, so we need to multiply that number by 2 to find the number of moles of hydrochloric acid. And then finally, to find the concentration, we do number of moles divided by volume. So that means our concentration is 0.188. Another student titrated sulfuric acid with barium hydroxide. Here's the equation. The student measured the electrical conductivity of the mixture during the titration. The better a conductor, the higher the electrical conductivity. Explain why the electrical conductivity of the mixture was 0 when the sulfuric acid had just been neutralized. Use the equation for the reaction and refer to ions in your answer. Let's have a look at these state symbols. Look, barium sulfate here is a solid, which means that there are no ions free to move. We've also got water present, which remember is a simple molecular or simple covalent structure, which remember according to their properties cannot conduct. The student then added a further 10 centimetres cubed of barium hydroxide solution. The electrical conductivity of the mixture increased. Give one reason why. Because it's in solution, which means the ions are free to move. So this is the last cheeky question about chemical structures. So how well do you know giant ionic, giant covalent, giant metallic, and simple molecular structures?